Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word: Breaking Math. Go to zencaster.com/pricing and use my code Breaking Math, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your.
What's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit a million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
A lot of the information in this episode of Breaking Math depends on episodes 30 and 31, entitled The Abyss and Into the Abyss, respectively. If you have not listened to those episodes, then we'd highly recommend going back and listening to those. We're choosing to present this information this way because otherwise we'd waste most of your time re-explaining concepts we've already covered. Black holes are so bizarre when we're measured against the yardstick of the mundanity of our day-to-day lives that they inspire fear, awe, and controversy. In this last episode of the Abyss series, we will look at some more cutting-edge problems and paradoxes surrounding black holes. So how are black holes and entanglement related? What is a holographic principle? And what is the future of black holes? All this and more on this episode of Breaking Math, and part 3 on a series of black holes. Episode 32, Gaze into the Abyss. I'm Jonathan.
And I'm Gabriel.
And you're listening to Breaking Math. You can find us on breakingmathpodcast.com, facebook.com/breakingmathpodcast. And if you'd like to support us, we have a Patreon. We're selling a poster from there that costs what?
$35.
Yeah, that's right. $35. And that's patreon.com/breakingmath, not patreon.com/breakingmathpodcast, as we've said before on the show.
Yes. And what's exciting is our first shipment of posters has officially been shipped. I'm so excited. I can't wait to hear from anybody who has bought a poster. Jonathan spent a very long time on them, and it has painstaking detail about tensor mathematics, which is used in Einstein's theory of general relativity.
Which, of course, is the most current version of gravitational theory that's widely accepted, and developed in 1916, so it's been holding on for a very long time.
What's also exciting is there's a Facebook page called The Credible Hulk. I don't know if any of you guys follow this page. He is generally affiliated with the skeptics community. He's also, into science. He spreads a lot of information about science and critical thinking. And we found out that, well, first of all, I'll mention his Facebook page has over 200,000 likes. I thought that was pretty darn impressive. I messaged him because I read one of his blogs about mathematics. He's really into math, so I thought, hey, maybe he would really enjoy one of these tensor posters. So I messaged him, and guess what? It turns out he lives right here in our home state of
Albuquerque, New Mexico.
Yeah, he goes to the University of New Mexico. So I literally just drove down to UNM, and I met him in the library, and we hung out. This was a couple days ago. By the time you hear this podcast, it was probably a week ago. You can go to our Facebook page at facebook.com/breakingmathpodcast, and you can see a picture of me hanging out with the guy from the Credible Hulk Facebook page. I'm pretty proud of that. That's pretty cool.
Yeah, and so what are we going to be talking about on this episode? What type of things?
So this episode is a very interesting one. Jonathan had mentioned that it's a pretty deep one. That's true. We're going to be talking about solutions to the Hawking information paradox, which we went over in our last episode.
Yeah, and we're also just going to be talking about some of the weirder, like less proven, more
esoteric.
Esoteric versions of black hole theory.
That's right. In fact, I think if I'm reading the outline, correctly, we're even going to start off with some of the strange ideas about black holes.
Yeah, and we'll come back to this idea later too. It's the idea of holium.
Black holium? What on earth is that?
So what that is like if you have a black hole that has managed to get itself less than the Planck mass, which is 21.8 or so micrograms, which is about as much energy as there is in about a really big tank of gas in a car. So you could imagine that being like something like less than that being just the tiniest little black hole that has no way of evaporating because it's too small, forming a stable type of matter. Some people even think it's part of dark matter, holium, because it has all the properties of dark matter. All it emits is gravitational radiation, the same way that excited phase transitions in normal matter are electromagnetic radiation.
This is amazing. So this is, I realize this is entirely in theory, but as you said earlier, in theory, you can have black holes that are just not big enough to evaporate. Can you clarify why their size or even their initial size would have anything to do with their ability to evaporate?
Yeah, there's a maximum size that, a maximum amount of energy that a photon can have, and that's 21.8 milligrams worth of energy. Remember, E equals mc squared, so energy and mass can be related, and that's how you get the amount of energy for this photon.
Okay.
And that's a photon with a wavelength equal to the Planck length, which is the smallest you could get in the universe. So if you have a black hole that's small enough, there might be no way for it to radiate energy because it's so small that its temperature would be too high to radiate out energy. There's debates on whether or not this is even physically a thing. This is only about 6 years old, this stuff.
Wow, I had no idea. Wow, so this stuff that they're calling black hole it's holium. It's
just holium.
Okay, and what was the resource that put this idea into your head?
Well, I got it from Wikipedia, but the people who designed it were K. Chavda and Abhit Chavda in 2002. Oh, okay, so it's 16 years old.
Okay.
I misread.
2002, that's when I graduated high school. So this is interesting. So you mentioned earlier that a photon can have a maximum energy that makes any sense in our physical universe, and that is a wavelength. Sorry, is it a wavelength?
Wavelength, yeah.
Okay. The size of the Planck length. Now, you had mentioned earlier that, prior to us recording this, that there is no minimum energy a photon can have.
Well, some people say that. Other people say it's probably the radius of the observable universe, or the diameter. I can't remember which one. But so it might change over time, which might make sense because the universe is expanding, and the expansion is, by our own measurements, accelerating.
Wow. How interesting. Okay. So now, is there any reason why this black holium would not exist?
There might be a way for... it might, for example, if a black hole is very, very small, it might just have a very small probability of radiating out small photons and things like that. Okay. So it might not be an absolute limit. We don't know much about the mechanics of black holes, especially when they intersect with the Planck length and things like that. That's where we go into a lot of confusion, is where the giant world and the tiny world intersect, because
Okay.
we have different theories governing both of them.
Now, you may have mentioned this earlier, but I'm still just very, very curious. For the sake of our discussion on this theoretical thing called black holium, what did you say was the size of a black hole that would not be able to evaporate?
21.8 micrograms, which is a very, very small amount. That's like a 50th of a grain of sand.
Wow. And then do you know what the radius of this kind of black hole would be when it first becomes a black hole?
It would be, I think, the Planck length.
Oh, wow. Oh, man, that's crazy. Okay. Wow. So, yeah, as you can see, there's a whole lot of strange ideas. And black holium is not the only, theoretical idea that comes out of black holes. There's all kinds.
Yeah, and we're going to be discussing a few of those on this episode.
Yeah. Although we are not going to do a full recap of the previous 2 episodes, should we do a very, very, very small recap just for our listeners who may not have listened to the episode in a while?
Yeah, sure. Information is stored on the edge of black holes. 1 bit of information is 1 square Planck length. And we'll be talking about that when we talk about the holographic principle. We're also going to be talking a little bit about, we're also going to be talking about the event horizon a lot. And the event horizon is it describes a sphere. The radius of the event horizon is how big the sphere is. And the property of the event horizon is that any event that happens within the event horizon could not, in theory, go out of the event horizon. So it's the point at which light cannot escape. So you can't send signals out of a black hole.
Yeah. And also, I'll talk a little bit about Hawking radiation, which we got into deeply in the last episode. Stephen Hawking was aware of some properties of quantum mechanics, specifically virtual particles. And I think it was Richard Feynman who first introduced virtual particles. Is that right?
I think that he had a lot to do with it, yeah.
Okay. When I first read about virtual particles, how shall I put this? There wasn't a lot of context given to them. That term stuck with me, and I tried very hard to read more about them. But frankly speaking, when you're in high school and you're learning about physics and chemistry, virtual particles are never really mentioned.
Yeah, virtual particles are a lot like potential energy. They're not real, but they have very measurable effects. Like if you hold a ball up, it has a certain amount of potential energy with respect to and it's different. Like on the surface of the Earth, it has a certain amount of potential energy, which is how much energy it will have when it falls to the surface of the Earth. Like a spring, when you press it down, has a certain amount of potential energy, which is the amount of energy that happens when you release it. And in the same way, virtual particles, a good model for them is that they pop in and out of existence in pairs. And if you take this to be literally true and ignore quantum physics for half a second, then this is a good description. They just pop in and out of existence if stuff blocks them joining together, because they pop out. They 2 different types of particles, an antiparticle and a particle, but a different type of antiparticle, like literally one with negative energy, emit from a point, and then they suck each other back into each other, and then they never exist. It's like as though they never existed.
And I think that with respect to virtual particles, they're called virtual because the average of their energy is 0. But that doesn't mean that they're at any given instant in time, the energy is 0.
In free space, in a solution where you don't have complexity at all, there's no detail to the universe, like just a blank space of the universe, then their existence sums up to 0, which means that they will not be detected from outside. Like if we have a sphere and inside of that sphere, space-time is flat, which never happens, by the way, but it's the ideal situation. You'll never detect a virtual particle from inside that sphere.
That's fascinating. One of the great descriptions I heard, and again I mentioned this on a previous podcast, the Ask Science Mike podcast. I think on one of them he was talking about a lake, in the early hours of the morning before anybody is playing in it at all. It looks like glass. It's almost perfectly flat. But then when you have people playing in it, it gets you get all kinds of wakes, and you get waves, and you get ripples, and all kinds of things. And with virtual particles, the fact is that in our universe, according to the laws of quantum mechanics, you've got fields that permeate all of space. And these fields are not static. They do fluctuate. And virtual particles can also be described as the fluctuations in the field. Is that a good roundabout description of these?
Yeah, and to tag on to that, let's say that we had a book, and we put it on the surface of this pond, and we took it off. you would see the edges of the book. It would look like a square, kind of like rippling out, right?
Yes, yes.
And you can imagine, like, if we took a book the exact same shape and size of the pond and pressed into the pond and then took it off, there'd be no, if it were perfectly flat, there'd be no place where a ripple would start or a ripple would end. It would all the ripples would happen at the same time, and thus no ripples would happen. That is essentially how virtual particles interact, because, like, if, for example, we changed the surface of the water at a certain place, it would change the way that it interacts with the flat thing, and it would not be flat at that place. So that's how virtual particles work. And to listen to more about virtual particles, listen to episode 31, Into the Abyss of Breaking Math.
Right, yeah. And then again, just for the sake of our recap, you had mentioned earlier that virtual particles can also be described as existing in pairs. Hawking radiation is the description of the event where you have virtual particles pop into existence right at the event horizon of a black hole, and that means that one of them will go into the black hole and one of them will go out of the black hole, and it will never annihilate. Therefore, it becomes a real particle.
Yeah.
So, but here's the funny thing. You're not really creating matter. We know that there's the law of conservation of matter and the law of conservation of energy, which means that energy cannot, both matter and energy cannot be created nor destroyed. They can only be transferred. So when you have these particles pop into existence and not annihilate, well, according to the mathematics, a little bit of the black hole that is the same size as the virtual particle that now exists as a real particle, that part of the black hole evaporates.
Yeah, and to go a little bit more into that, I think that, I have a personal theory. It's not a very widely accepted theory, that the interior, like the event horizon, I don't think anything really exists. I think talking about what exists inside of a black hole is essentially silly. And I think that this points to that, because the longer a virtual particle exists, the more it becomes like a real particle. So it can't have negative energy anymore, for example. It takes on positive energy.
The whole idea that a virtual particle can have negative energy, I hear the words that are coming out of your mouth, and they make sense in terms of, like, a sentence with proper syntax and grammar, but what on earth is negative energy? I mean, what the definition of energy is the ability to do work. So is negative energy that what does that even mean?
That's a work debt. So it's like a work request. It's like billing somebody for work. The universe is really a big accountant.
That's insane. That is absolutely insane. Yeah.
So if you think about it, like, if this virtual particle turned into two particles, the one in the middle would be observed differently than the one on the outside. Yeah. So either black hole complementarity exists in a way different than we think it does, to me, or just the inside of a black hole is a silly thing to talk about. And I think it's a silly thing to talk about because quantum physics tells us that if we can't measure something, then it's silly to talk about it. And honestly, I think that we just need to apply that to space-time not just singularities, but event horizons.
So is this Jonathan just, lifting up that rug and sweeping the whole question? I'm just kidding. I'm just kidding, man. Yeah. So
I destroy things on principle, not because of shame.
Very good. Now, the idea of Hawking radiation and the eventual evaporation of black holes brought up what we discussed in our previous podcast, and that is Stephen Hawking's information paradox. And the whole idea is information ultimately scrambled, or is it ultimately completely destroyed such that it never, it's as though it never existed to begin with? Now, the latter has some very, very scary consequences, but we've already discussed that, so I'm not going to go into great detail here.
Yeah, the biggest one, meaning that if you run a black hole in reverse, it's as likely for radiation to come out as a kitten.
Yeah. In other words, it's essentially nonsensical, and that's, physicists like causality. Physicists like things being able to be described and predictable. So destroying information is a big no-no. It's almost like the ultimate practical joke that our universe is, because it makes no sense at the end.
Yeah, under our current definitions and things.
Now, what's worth mentioning, in our research for this episode, this was an amazing episode to research for. All the thought that has gone into this is just mind-boggling. So what's fascinating is right now, if you ask any physicist who's working on this problem, the information paradox is considered solved. It is, I'd say, widely accepted that information is not, in fact, destroyed. However, what's very interesting is, although that's accepted, you could say thank God for that. It's what's not accepted is entirely why. As we have prepared in this episode a few things to talk about and a few possible solutions to the information paradox, and some of them, I don't mind saying, are a little out there, but it's certainly considered a fact that information is not destroyed. So in this episode, this final episode in the series, we're going to talk about the 3 or 4 or more models that try to explain why the information is not, in fact, destroyed.
Yeah, and without further ado, here's the rest of the episode. So what we're going to talk about right now is complementarity, the no cloning theorem, and the no communication theorem.
Yeah. So I think that the first thing we'll talk about is the origins of this. So almost immediately after finding out about the information paradox, the physicist Leonard Susskind, as well as Gerald, how do you say his last name?
I think Tooft.
I'm so sorry.
I'm not editing that out. You have to live with that.
Okay, T'Hoof. I'm sorry. His last name
You're
is...
just digging a hole.
I know. So almost immediately, they came up with something called complementarity. Now,
they didn't come up with it. It's a quantum physics thing.
Okay. So I'm going to give you my definition of complementarity, and then Jonathan, I think you should give your definition. Complementarity is when you have two models that can describe something. Like you can have two mathematical models that describe a phenomenon, and they seem to contradict one another, but they both accurately describe something. And the thing is, they can both be found to be true depending on how a phenomenon is observed. Now, this actually exists. You want to add anything to that?
Yeah, like what we could talk about is position and momentum, because it's easiest to understand using just a simple model. So let's say we're at a shooting range and we don't have our glasses on, so we can't see anything down the range, but we know that there's a ball moving around, and it's moving. We know that it's moving, and we receive this information very quickly, and we start shooting bullets as fast as we can at this ball that's moving down the shooting range. If we look at how the stuff scatters off of the ball, we know exactly where the ball was, but because the bullets are so powerful, I mean, they put a hole in a man's chest, they're probably going to move the ball so much that we don't know what its momentum was to start with. However, if we just shoot very light bullets at it, we could look at their deflection, measure the momentum, but because the position is being measured so inaccurately, because we have to fire a lot of tiny bullets over a lot of time, we don't know its original position. So position and momentum are considered complementary, because if you either know a ton about the position or a ton about the momentum, or a little about both, if we know that we can know X amount about the position and then Y about the momentum, we can't know both at the same time.
Yeah, and actually, I know exactly what you're talking about, Jonathan, because in the case of photons, let's replace the bullets in your example with photons. The thing about measuring things, the only way that we can have information about something is to measure it. But when you measure it, it requires seeing it or detecting it somehow.
Interacting with it.
It requires interacting with it. So, if you look at it, you have to have light bounce off something and then reflect and go back to your eye. Well, frankly speaking, you've changed it by a photon touching it. So it's no longer in the same state that it was before the photon touched it.
Yeah, it's related to the Heisenberg uncertainty principle, and a lot of that can be thought of from a macroscopic point of view. Like, if we have a beaker of water and want to know what temperature it is, we could put a thermometer in there, but the thermometer is probably going to be a different temperature than the water. So we're going to change the temperature of the water by measuring it. Same thing with measuring something's length. You might think that a ruler is a perfect way to measure something, but even the presence of the ruler is going to, like the temperature of the ruler is going to cause expansion or contraction of the thing that's measuring. It's going to change the geometry of space-time around it. There's no way of measuring anything without changing it.
And so that's one aspect of complementarity, so you might say, okay, fine. So you don't know exactly what temperature something is when you measure it. The thing about it is, though, it gets really, really weird. And I'm specifically referring to the double slit experiment. When we're talking about complementarity, we can talk about light, or even other particles
Electron
of matter.
beams.
Yeah, electron beams, or even DNA itself.
Although you'd require an incredibly high energy beam for DNA.
That's true. All of these things can be described as being either a wave or a particle. And before the double slit experiment, and before it was done properly, by the way, that experiment I think was described as the most beautiful experiment in all of physics of all of time, because it clearly illustrates this principle. This double slit experiment, and again, that's a pretty popular experiment. It essentially showed that light is either a wave or a particle, depending on how you measure it.
Yeah, and the double slit experiment, just real quick, let's imagine you have a very still bathtub, and let's imagine you have two pencils about a foot away from each other, and you start bobbing the pencils up and down, creating waves. They're going to kind of crisscross and create kind of a trellis type pattern, right?
Yeah, you're going to have the ripples that are going to spread out.
And cross with each other,
Yeah,
right?
interference. Yeah.
Yeah, and so if we had a board at the end of the waves, we could measure how high the waves are, and it would be something that would be kind of a ripple. It would start like if you do frequency equals amount, basically.
Yeah.
So it would be you'd have an interference pattern. It wouldn't be the same as if you just did one of them or the other one.
Yeah, exactly. So and you've got constructive interference, and that's when you've got two waves that come together and their amplitudes are added together. You get a giant wave.
Yeah, so that's like if on the left pencil there's a certain place where the wave is high, and the right pencil without the left pencil in the same place, if the wave were high, both pencils together, the wave will be twice as high.
Yeah, or twice as low if you've got two of the troughs that come together.
And of course, if one would be high and the other would be exactly as low, then the level is the same as the level of the water.
They cancel that to zero. So yeah, that's clearly unambiguously a wave.
Yeah, and so if we start with the wave kind of further back, so let's take the two pencils and let's go way far back, so that we have both pencils about the same far backness as a point pretty far back in the bathtub. So you're at the start of the bathtub and the two things are next to the drain, basically the whole thing that we had set up. Now, if we replace the 2 points where we were making the ripples with a wall, but to put two spaces where the ripples were being generated, then when we generate ripples from our point really far back, it will ripple out through the spaces and create little tiny ripples, and they'll interact the same way. So you'll have the same pattern on the end of the bathtub, right?
Yeah. Exactly.
Summer concerts, pool parties, chill nights under the stars. We're stocking up our closet so you're ready to look your best for all of it. At Plato's Closet in West Ashley and North Charleston, we're buying all things summer. So bring in your tees, tote bags, sandals, sunglasses, and more. We pay cash on the spot for gently loved name brand looks. Plato's Closet is the go-to destination for trend-forward teens and young adults who support local and shop sustainable. Visit Plato's Closet today. Plato's Closet, located in West Ashley on Sam Rittenberg Boulevard and North Charleston on Rivers Avenue.
America. We are endowed by our Creator with certain unalienable rights: life, liberty, and the pursuit of happiness. At Grand Canyon University, we believe in equal opportunity, and the American dream starts with purpose. To serve others in ways that promote human flourishing and create a ripple effect of transformation for generations to come. Find your purpose at Grand Canyon University. Private, Christian, affordable. Visit gcu.edu.
And so with and the rule is for quantum physics is that the height of the wave, no matter if it's positive or negative, gets squared. And the square of the height of the wave is the probability that a particle will exist there. And so the double slit experiment is really simple. You just take a black piece of cardboard or something, well, something thinner than cardboard, and then you take two razor blades, put a little thin piece of something between them, and you cut the fabric, and you shine a light beam through it from far away, and you'll see a ripple pattern at the thing that it projects onto.
Yeah, pretty much, yeah.
But if you even send one, and they've done this with, if you replace the holes in the sheet with two reflective little strips of nickel, and you fire electrons at it, then the electrons will cause the interference pattern. But if you slow it down so they have just one electron going through at a time, it'll have the same pattern.
Yeah. So it's, you would think that would be unambiguous proof that light travels as a wave and not as a particle. But it's just weird because you can't describe everything that goes on with light as only a wave. I mean, Einstein talked about little packets. Like he specifically talked about packets of light when he was talking about the
photoelectric effect.
Yeah, exactly. That requires packets of light.
Yeah, and the photoelectric effect, just real quick, is if you take 2 sheets of gold leaf that are charged with the same amount of charge, if you shine all the red light you want, you could turn the sun into red light and shine it at this, and they will never come together. But you shine a little bit of ultraviolet light, just a tiny bit, and they'll come together. And it has to do with the way that the particles interact, but it shows that stuff travels in quantums. There's a minimum amount of, there's packets of energy.
Yeah. That's crazy. So the thing is, you have these physicists who designed these experiments who basically said, now I know that light travels, in packets. I know we see it as a wave, so I'm very curious. What happens if I put a little sensor, any kind of a light sensor by one of these 2 slits? I want to see if I can measure the light as it goes through one or the other. The wild thing is, and the point we're trying to make with this entire section of this podcast on complementarity, is that as soon as somebody, as soon as the scientists designing the experiment try to measure what goes on at the slit, it no longer behaves as a wave. It behaves as a single particle only going through one of the slits or the other.
Yeah, and you could do that by light can be polarized. I mean, when you go to the movie theaters and you watch a 3D movie, the light from the left eye is polarized, let's say left, up, left and right, and the right one is up and down. So if you have a polarizer that's left and right in your left eye, it'll only let the stuff that's left and right into your eye, and it'll block everything else. But if you have an up and down polarizer in the right one, nothing will go through. If you did it at 45 degrees, like a diagonal angle, then it'll let half of both go through. That's why you can't turn your head when you go to the theaters. That's why it causes a lot of neck strain.
Yeah.
But so let's say we had the 2 slits and we put a vertical polarizer in front of one and a horizontal in front of the other one, so that when it hits the wall, what we could do is have another vertical polarizer and then just measure whether or not it went through the left or the right one. Giving it that information means that it no longer looks like a ripple. It just looks like 2 fuzzy dots next to each other.
Yeah, and this so I think that in the history of science, this was a moment that, almost like sanity just went out the window, or rather, the sense of familiarity. You know what I mean?
Oh yeah, and here's the bizarre part though. If we put a diagonal polarizer after the 2 polarizers like the experiment that we just did, we put a diagonal polarizer in front of both of them, thereby erasing the information. It's a double slit pattern again.
That's just weird. So things don't behave the way that we would expect them to. Now, that is the namesake of this section. It's describing things in our universe in a complementarity, that's the term.
Yeah, complementary way, complementarity-based way.
In a complementarity way, where you have 2 different ways of describing something, and the key description here is that they're both true. So what does this have to do with the Hawking information paradox and how information might be conserved?
Well, we got to talk about the no cloning theorem to talk about that.
Okay. So just so that our listeners are keeping up. So we're going to talk about how information might be conserved with this whole idea.
Well, how it definitely is conserved.
Okay, how it definitely is conserved with this whole idea of complementarity, and what it has to do with something else called the no cloning theorem. So hang on tight.
Yeah, so then basically we got to talk really quickly about entanglement. If 2 particles that are entangled, like let's say I take a photon and entangle it, that means I create 2 lower energy photons that they both, no matter how far away from each, so I could send one to Alpha Centauri and keep one on Earth. And as soon as I measure any property of my particle, I will know, if I was very careful about my accounting and what I did to that particle, I would know the state of the one that was in Alpha Centauri immediately. Meaning that, like, if I sent entangled particles to Alpha Centauri every year, then we could do something like, let's say they needed a certain type of supply, and they measured the particle, thus letting me know that they needed that supply. I think it might be the case that we could increase the efficiency by twice, but I would have to double check that.
Interesting. And I know that entanglement is a fairly popular idea. It's another very, very, very weird idea, and it's, so you said earlier that for entanglement to happen, you have to have two particles in close proximity. Do you know at what point they become entangled?
I think they become entangled in as much as the other properties are shared, are coherent, because entanglement and coherence are complementary themselves.
Oh, wow. Interesting. Now, I know that entanglement, this is just a quick sidebar. I know that entanglement with electrons can happen as soon as they share a shell. I almost had a tongue twister there.
Yeah, and what's interesting, though, is that entangled electrons are different than entangled photons.
Really?
Because entangled photons will have the same property as we talked about in our Bell episode, but entangled electrons will have opposite properties.
Wow. Okay. So really, this shows that entanglement is not just something with one. Like, it's not related exclusively to the Pauli exclusion principle. It's just if two particles interact in any way, they can become entangled.
Yeah, and real quick, the reason why we can't send a signal faster than light is, let's say we entangle a particle here and one on Alpha Centauri, and then we wanted to, let's say we wanted to send a signal at the exact same time here in Alpha Centauri, and so we measure our particle. They cannot, if they measure their particle at any time, then they are the ones who make the particle one thing. So this leads us into no cloning theorem, because if they could clone the state of their particle, then they could just keep firing off clones of it and then see what their states are. And if they're random, then that means we haven't measured our particle. But as soon as we measure ours, it would become the same one every time, which means that we'd be able to send a signal faster than light and thus violate causality.
Okay, so let me slow down real quick here. So we're talking about two things here, and there's a small difference here. We're talking about sending, or rather having information faster than light, and then we're talking about signals. Now, there's a difference. As Jonathan said earlier, you can get two particles and you can entangle them and not measure them at all, not measure either one of them. And as Jonathan said earlier, you can send one off arbitrarily far, light years and light years away. If you measure one, then automatically you've got information about the other one. So you may know something about it, which is interesting because, if you haven't measured it, how do you know if an electron is spin up or spin down? Well, if it's entangled with your electron and you measure your electron and it's spin down, then you know for a fact that there's an electron far, far, far away that's spin up. But as you said, you can't send a signal.
And not only that, it's very hard to send time information, because let's say I sent one particle to Alpha Centauri, which is 4 light years away, saying that if 5 years in the future some event happens, like let's say bread is less than $1 per pound, then I measure my photon or whatever particle I have, and so when I measure mine, they know theirs. So what they could do is they could agree that happens, but the way that it works out, they would have to confer with us. So there's no way of knowing whether or not they we can't go into the math, and we'll go into another episode, but you have to confer with the other particle, so you cannot send information faster than light no matter what.
Yeah, and then so essentially the no cloning theorem can be said another way, the no communication theorem. You're not going to be able to send any kind of like a Morse code signal via entangled particles at all.
Yeah, and just real quick about the entanglement thing, if two particles are entangled, you could think of them as having instant communication, quote unquote communication with each other. So you can almost think about it like, let's say we have ours and the one on Alpha Centauri. Let's say the one on Alpha Centauri gets measured. This is the way that I think about it personally, and it helps me a lot. All of a sudden, time reverses from Alpha Centauri because it's measured there. All of time starts reversing, and then in the light cone, which is the sphere expanding at the speed of light from the center of Alpha Centauri, time starts reversing. So it sends an anti-time signal until the origin of when the two particles were entangled, and wherein it goes forward in time again. And you don't have to think about it that way, but it helps me.
Did you guys catch all that? You all caught all that, right? You're following? Okay, good.
Maybe it wasn't very coherent.
It's not good,
unlike
dude.
entanglement.
Can you just go back in time and listen to it again? You know what I mean? Like if you're entangled with this podcast, I don't know. Okay, so the question is then, if you're Leonard Susskind, the physicist Leonard Susskind, who is a professor at Princeton, and you're trying to explain why information is not destroyed in black holes, how can you use this idea of the no cloning theorem and also this whole idea of complementarity to prove that information is conserved when black holes evaporate?
Well, the no cloning theorem actually presents a problem for black hole complementarity. But black hole complementarity basically states that there seems to be two things that happens to information when it hits a black hole. Either it gets kind of like scrambled up and put on the surface, or it goes through the black hole and nothing seems to happen at first. Like if it's a supermassive black hole, the equations say that you wouldn't even be able to tell once you pass through the event horizon.
Okay, so let's just go through these one at a time. I'm gonna slow down real quick. So let's pretend, as you said earlier, in the example of a supermassive black hole, if you are driving a spaceship and or whatever, if you're just by yourself and you're going toward a black hole, you're not even going to notice when you cross the point of no return. Is that right?
Yeah, and here's the thing, because it's a point of no return, once I'm past it, I can never send a signal out. But once I'm out of it, basically once you're in, you can never become out again. And once you're out, you either become in or you stay out. So they seem to be separated. And complementarity is, because of a complicated reason, something that you could look at. And spaghettification happens in the middle of black holes and near the singularity, which is the point at the center.
Okay.
And that's where gravitational forces, like let's say you fall in like feet first.
Okay.
The gravitational force near your feet, when you get close to the center of a black hole, with the current equations, would be so much greater than the force at your head that you'd be stretched, as Stephen Hawking says, like a piece of spaghetti.
Interesting. Now, real quickly, as we're talking about complementarity, when you talked about once you're out, now I don't mean once you're out as though you can be in a black hole and then suddenly you're out. That's not possible. Rather, let's talk about what happens if you are an observer who watches something go into a black hole. It's entirely different, and this is just weird.
Yeah, it's almost like let's say you had a book with like that it was just written in watercolor, and you take a page out of it and you dip it in the sink, and as soon as you dip it in the sink, all the information spreads across the surface. That's what we predict would happen if you see something falling into a black hole. It would just scramble.
Okay. So again, we've got two perspectives here, and these two perspectives are complementary. Are complementary. One perspective where if you are the person going into the black hole, what you'd experience, and then one perspective is if you are far outside of the black hole and you see somebody else go inside. And
well, possibly complementary, because if they violate the no cloning theorem, they cannot by definition be complementary.
Okay, you're right. So then let's talk about why. So Leonard Susskind proposed this idea that information is conserved because of complementarity. Now, did he think that the information is conserved because as you're watching something go into a black hole, the information is, well, obviously whatever it is like burned up. I don't want to say burned up, but destroyed, and all the information.
Well, that's not just to be very clear. It's not destroying information.
Okay,
scrambling information is just increasing the entropy, and that's perfectly legal in physics.
Cool. So he basically says that information is conserved with black holes because they're complementary. Because of complementarity, and as long as you're the person who's watching it happen, whatever went into it, that information is now scrambled on the outside of a black hole. So is that the conservation of information?
Yeah, the reason why that's a potential solution is because the whole thing with Stephen Hawking's information paradox is once it crosses the event horizon, there's no way of retrieving the event, because you can think of causality as being strings that are connected by light.
Okay.
Light is the fastest as stuff can go. So everything's connected by this light or virtual light or like pseudo light, whatever you want to call it.
Okay.
So when something falls into a black hole, because light cannot escape, information cannot escape. Because remember, information, the things that relate cause and effect, that is information.
Okay.
So if black hole complementarity exists, then the surface of a black hole, or the exterior surface, which is proposed to be one Planck length above the surface of a black hole, contains all the information. But once you pass that, you still retain all of your information. So it lets every reference point retain its information. It lets every reference point retain its mass and where the mass goes. and the 2 points cannot be, well, they can kind of, we'll talk about in a second, communicate together, so they are complementary.
Okay. Now, for our listeners, just so that we're tracking here, yeah, this is weird. This is
it's very weird.
This is really weird.
This is breaking edge. This is like, if you could solve most of the stuff we're talking about in this problem, then you could write a paper.
Okay, so for the sake of our listeners, I just want to point out that complementarity is really, really weird. And it involves, when you can describe something 2 different ways, like waves or particles. And Leonard Susskind had the whole idea of applying that to black holes and saying, well, as long as you're seeing an object that goes into a black hole, as long as you're seeing it get evaporated on the surface of a black hole, the information is conserved. So I don't know.
Well, the reason why black hole complementarity is probably proposed is because of the no communication theorem and no cloning theorem. Essentially, they modeled a black hole as a quantum interaction, which involves a thing called an S matrix. You look up more on that. It's too complicated to go into. Yeah,
in fact, I think Leonard Susskind talks a lot about the S matrix in his book, The Black Hole War. Just to give him another plug, it's a good book. It's wordy at points, but he's got so many diagrams, and it's really not terribly hard to understand.
No, it really isn't. And so basically, he just looked at, there's a prediction about what happens to stuff falling into a black hole. When you look outside of a black hole, there's a different prediction for when you're inside of a black hole. And also, there's a difference between the inside and outside of a black hole that involves information. So therefore, they must be complementary. And that's really not that weird of an assumption to make. It goes off of a lot of philosophical reasons for quantum physics.
Yeah, it's just still, whether it's the double slit experiment or black holes or anything else, complementary is just weird.
Yeah, but one thing that the Monty Hall problem, which we covered in which episode was that?
Monty Hall, it wasn't QED, was it episode 7?
I don't think it was QED. We covered the Monty Hall problem, which you can look up online. It's an incredibly unintuitive, but very, very, very simple problem. And if that could be unintuitive, then black holes have all the rights in the world to be unintuitive. The next thing seems unrelated at first, and to a lot of you, and even to us, will seem a little unrelated still after we go over everything. But it's called the holographic principle.
Yeah, and this is an interesting one. I actually first heard about this, I think it was from the documentary, although there's numerous documentaries I've seen that go into the holographic principle. One of them is the one on the BBC on the Hawking information paradox. You can Google it and probably find it. I've also seen it on the Science Channel, in fact. There was I think it was called Through the Wormhole, narrated by Morgan Freeman. They talk a lot about the holographic principle in that show, too. So how would we describe the holographic principle?
Well, first, let's imagine we have a library. Let's say it's a Smithsonian or a museum, whatever, something with information in it. And we could draw a sphere with a radius of a certain radius around that museum, right?
Yes.
And that museum would not have enough mass to create a black hole, right? Because it exists.
Definitely. Yeah.
Meaning that if we kept making that library more and more dense, there'd be a point at which it forms a black hole with that radius.
Okay, I'm definitely following you so far.
Now, because a black hole has a certain amount of entropy that is defined by its surface area, and remember, the surface area of a sphere is equal to the square of its radius times 4 pi.
Yes.
Whereas the volume is the cube root of the radius. Now, to give you a difference between the square and a cubed, 2 squared is 4, while 2 cubed is 8. 3 cubed is 27, while 3 squared is 9. So it gets bigger way faster.
Yes. So this is the interesting thing is the whole idea of a holographic principle, I think, essentially emerged first with black holes. If it weren't for black holes, we would never have the holographic principle.
Yeah, and we've talked about zeros before on this show. I think we talked about it in QED, episode 7 or so.
Yes, that's correct.
We talked about how zeros and infinities usually tell us new things. Even with quantum physics, it was the calculation that it often had infinite energy that led to the discovery of quantum physics.
Yeah. Now, as you're talking...
Which is also obviously false, but...
Yes. As we're talking about the black hole holographic principle, this was, I believe, first introduced, at least one of the two physicists was Leonard Susskind.
in conjunction with Bekenstein.
Yeah. And again, what this has to do with, and it may even be smart, or it may be wise for us first to talk about what a hologram is and why it applies.
Yeah, a hologram. Okay, the first, like, a hologram, when people think of it, is a 2-dimensional object that has 3-dimensional data. So, like your driver's license probably has a little thing on it where you rotate it and it changes color. That's a very simple hologram, and it has technically 3-dimensional data because you could imagine a surface that it reflects light based on the angle that it comes in. But a more complicated hologram could be one of those that shows a 3D object. The holography in mathematically just says that you have one dimension representing another dimension in a certain way entirely.
Yeah, and the reason why you can arrive at the holographic principle with black holes is because with a black hole, it's impossible to get any more dense than a black hole. You can't pack any more information in a black hole. So when you put more stuff in it, the black hole inevitably grows because you're not going to get any more packed.
Yeah, meaning that if you made a black hole out of the highest entropy stuff that it could be made out of, it would not change entropy when it turned into a black hole.
Yeah.
All the stuff that was already scrambled enough.
Yes. So specifically with a black hole, because you can't pack any more entropy and you can't pack any more information in the volume of it, it can be said that all of the possible information that describes the stuff in a black hole can fit on the surface area of a black hole.
Yeah, and the thing is that because a sphere, for a certain amount of surface area, has the least amount of volume.
Yes.
And because a Schwarzschild black hole is spherical, it means that no matter what bounding, so let's say we had a duck-shaped volume of space. The surface area of that duck would be more than is needed to encapsulate everything in there, and a sphere would be the least amount. So basically, it's lowest upper bound on the information of the stuff inside. And remember, we talked about how information is encoded in Planck units, almost like pixels on the surface of things.
Yeah, and what I love about the holographic principle is how, I don't want to say easy it is to arrive at, but it's not intuitive. Like I wouldn't have thought of it,
Yeah, and it depends completely on the fact that black holes have entropy.
Okay.
But here's the weird thing about it, is that we have a thing called natural units. Natural units basically set a bunch of fundamental constants, which we've talked about a lot on this show, to 1. So the gravitational constant, instead of being like 6 times 10 to the 23rd, negative 23rd or whatever it is, it's equal to 1. The Boltzmann constant is 1. Speed of light is 1. The Coulomb constant is 1, and the Boltzmann constant is 1. Now, you always have to have other constants, like the 2 remaining, based on the fine structure constant and the gravitational fine structure constant, but you can set a lot of this stuff to 1, which means that in this set of natural units, instead of the radius of the black hole being g, the gravitational constant, times m divided by c squared, it would just be equal to m, because everything just turns out to be 1.
Yeah, that's interesting. I'm not sure I'm entirely following. Can you?
So, like, let's say, like, g, instead of c being like meters per second, what we do is we define a meter in a second in such a way that instead of having 300 million to 1 meters to seconds, we just have 1 to 1 distance to time.
Okay.
And you could define the gravitation. You could define up to 4 of these constants of the 6 or so that are the universal constants. Make them equal to 1.
Okay, interesting. Now, let me ask you real quick. One thing that I'm still not quite clear on is, although I certainly understand the holographic principle, and I understand that information that goes into a black hole can be stored on the surface of the black hole, what does that mean for when a black hole evaporates?
Well, what that means is that because when a black hole evaporates, its entropy goes down, and it gets the entropy doesn't go down in the whole universe; it's evaporated away. So the entropy goes elsewhere. So that's all that's saying.
Okay. So then, so I guess my question is, I know that in documentaries I've seen about Leonard Susskind and his solution to the information paradox, Does this holographic principle actually serve as a viable solution to the information paradox?
No, it's just a property of space-time, really.
So that's just some gee whiz fun information for you guys. Now,
Well,
you
not
know.
just gee whiz fun. It tells us something very fundamental about the way that mass is structured in the universe. Like, we've talked about neutron stars and how incredibly dense they are, right?
Yes, yeah, we have.
And that's a star made out of neutrons. And if you remember, a neutron is an atom is made out of neutrons and protons in the middle, have some electrons spinning around it, which are much, much lighter than the protons.
Yep.
Those protons are obviously very dense.
Yes.
If we had a mass dense as protons, that was about, I think, is the Chandrasekhar limit. I think it's like 3.4 solar masses. It would turn into a black hole, meaning that density, you can't have that density everywhere. And we'll go into the math real quick. So if the radius of a black hole is the mass, let's just call that m, what's the area of the surface area of the black hole?
I'm sorry, say that again.
If the radius of our sphere that defines our black hole is m,
Okay.
what is the area of the what is the surface area of that black hole?
Okay, so that's just the surface area of a sphere in this case.
Yeah, which is 4 pi m squared.
Okay.
Which means that the volume of the black hole is 4/3 pi m cubed. If we divide the mass of the black hole by the volume of the black hole, we get 3 divided by 4 pi times m squared. So m squared is on the bottom of the fraction. Now, what does that all mean? If you work it out, it means that the bigger you draw, let's say we have a random universe. You draw a sphere that has a certain radius. The amount of stuff that you could put in that is actually inversely related to the radius squared, meaning that we could actually draw a fractal that has some of the same properties as the universe. It would be very, very dense at small scales, but the more you go out, the more stuff is spaced apart. And that's the holographic principle. It's pretty amazing.
Yeah. And also there's some practical consideration for, like even us, like our information could be on some hypothetical surface of the universe too.
Yeah, and actually just talking about the universe, the observable universe, the radius of our universe from our measurements and calculations and science and everything we've been doing in the last 100 years is about 8.8 times 10 to the 26 meters. Now, a black hole that would be able to contain all that mass that we've been able to measure in the universe would have a radius of about 7.4 times 10 to the 25 meters, meaning that there's about 11 times as much radius as we need in the universe to not violate this. So even the universe itself obeys the holographic principle, meaning the universe is very, very not dense, because some black holes, if you measure their density, if you created an object of that same density on Earth, it could float in water. Some could even float in air.
Wow. Interesting. And yeah, that'd be like on the super massive scale. So when we brought up the no cloning theorem, the reason why we brought up this, as well as the description of entanglement, is that this has to do with something called the firewall paradox with black holes.
And the firewall paradox basically says that, when stuff enters a black hole, it seems like it's not that the information is very, very highly scrambled and stored on its surface, because, black holes have a certain amount of entropy. Now, here's a weird thing, and we've talked about this before, is that in general relativity, black holes have no entropy whatsoever. So entropy has to be a quantum property, which led, after a lot of work, Leonard Susskind and 't Hooft and friends, to say that a black hole's event horizon has a horizon right above it, one Planck length above it, which has the property that scrambles information that goes into the black hole, but black hole complementarity might exist at the same time. So you can imagine going through like a magic mirror. Like when somebody jumps into this magic mirror, we see the magic mirror just go crazy and start showing static and scrambling around them. But the person jumping into the magic mirror feels himself going to Alice in Wonderland.
Yeah, it's something quite wild.
Summer concerts, pool parties, chill nights under the stars. We're stocking up our closet so you're ready to look your best for all of it. At Plato's Closet in West Ashley and North Charleston, we're buying all things summer. So bring in your tees, tote bags, sandals, sunglasses, and more. We pay cash on the spot for gently loved name brand looks. Plato's Closet is the go-to destination for trend-forward teens and young adults who support local and shop sustainable. Visit Plato's Closet today. Plato's Closet, located in West Ashley on Sam Rittenberg Boulevard and North Charleston on Rivers Avenue.
Here's a weird thing about the firewall paradox, though, is that because we talked about entanglement before and how particles that are entangled share properties forever until one is measured.
And I want to mention something else as well. We had mentioned specifically that in order for two particles to be entangled, they have to be in very, very close proximity. Now, we deliberately didn't talk about exactly what happens that causes those entanglements. I believe they just have to interact.
Well, they have to have other properties which are kind of shoehorned in. So, like, for example, two electrons in the shell of an atom, which they're entangled because everything else that they share is exactly the same. So it's almost like the pigeonhole principle. They just are pigeonholed into sharing a lot of things, and the longer they're in that state, the more likely they are to be entangled, from my understanding.
You know, one of the things I want to mention is radical paradigm shifts as soon as new information is considered. And this information is sitting right under our nose. I don't mean information like a pun, like information paradox. So, you know, in previous episodes, we talked about the fact that, you know, black holes have high entropy. And we just talked about this whole idea of entanglement. Now, entanglement was known about when Stephen Hawking introduced his information paradox that's based on virtual particles. But something that was completely overlooked at that time, at least the way I read about it, is the whole idea that virtual particles themselves, when they pop into existence, they pop in from the same point. Therefore, virtual particles are entangled. That's very, very important, because if they are entangled, they share something in common. They share some information in common. At least, you know, if you measure one of them, then you have information about the other one.
Now, here's the thing, though. Once you measure one, the other one is irrelevant because they're entangled. But that is very true technically.
Yeah. So you know, the fact that this is not brought up until, gosh, you know, as late as 2012, that's when the firewall paradox was first published and first discussed. Fact is, when you have one virtual particle go into the black hole and you have one go into the rest of the universe, that entanglement is what's responsible for this firewall.
Yeah, and essentially you could think about it this way. Like, if we send a photon into a black hole, that photon has a certain amount of momentum. So the black hole is going to move a little once we fire the thing into it, because the black hole is like anything else. It could still be affected by forces. We can move a black hole around. We can use it as a battery if we want to.
Yeah. And so really what we can say is the information that goes into a black hole. Now, this is different from the holographic principle, which we also talk about in this episode. But when you consider entanglement, the information from the contents of the black hole is well, at least in terms of the virtual particles, that information is entangled into the horizon of the black hole.
Yeah, so we could think about, and here's the weird part, and here's the firewall paradox. Let's say we sent a particle across the event horizon. So now, like, that particle, let's name it Alice, is entangled with the black hole whose name is Bob, and the thing, and Bob is entangled with, and Alice is now inside the black hole, still entangled with Bob. Now, Bob, via Hawking radiation, which we talked about, emits Charlie, which means that since they're entangled, and since the original two are entangled, that means Alice has some properties in common with Charlie. Now, if we take Charlie and send it back into the black hole, then we could communicate between Alice and Charlie, because the thing is that since they're entangled and now they're going into the same place, Alice and Charlie contain the same amount of information, which means that at any point that we reflect Charlie from the outside of the black hole, our decision to reflect or not the particle into the black hole is communicating information into the black hole, which means that we could tell somebody inside the black hole stuff that's going on outside of the black hole and have it violate causality. We could violate space-time.
We talk about this. This is in violation of the no cloning theorem, essentially.
Yeah, and I will say that my solution that the inside of a black hole doesn't exist because it's space-time being unknit actually does seem to solve this.
Now, wait. Is this, sorry, for the sake of our listeners, is this the first time I don't remember if we discussed this before the podcast or actually on the podcast?
I think we discussed it right before the podcast.
Okay. So, but, you know, as we're planning this episode, Jonathan talks about his solution for the black hole, where, as you said earlier, it's not even worth it to discuss anything at all with respect to what happens inside the black hole. Like, it doesn't exist.
Yeah, and just to talk about that, there's another paradox where, let's say we have a shell that has enough mass to become a black hole when it's 1 light year in radius. But we make it 1 light year and 1 year in radius and 1 mile in radius. So it's a little bit bigger than it's supposed to be. Now what we do is that we make sure that at a certain pre-given time, it all fuses together at a small enough radius to create a black hole. General relativity tells us that at that instant that happens, event horizon will start forming where the singularity is and start expanding at the speed of light. Meaning that if we measure some event that happens at time t in the future with respect to creating the like, let's say we have some reference time and we say like, okay, if Central Park is 30 degrees Celsius or more, then we send a photon in, then we make sure that the black hole collapses. And we could do that using a complex wiring, making sure that all the black hole goes at the same time. Now, with the general relativity equations, we've just sent information a year in the future into the center of the black hole, because as soon as they measure light coming out of the center of the black hole, which happens right before they die or at least get trapped by the event horizon, then they know something that happens about the future. They can never tell us about it, but they know it. But it still violates causality in the quantum sense.
So essentially, we've exchanged the information paradox for a new one called the firewall paradox. And there's not really agreement about how you solve this firewall paradox. And again, as Jonathan said, his idea that something no longer exists when it crosses the event horizon, that's just that still causes a knot in my stomach. I got to be honest, I don't like thinking about non-existence, and the fact that you have a spherical, roughly, you got an approximate sphere that doesn't exist. But you know what I mean? Like isn't that weird?
Yeah, I mean, my view is that if you can't measure it, then talking about whether it exists or if it exists or the shape of its existence is perverse in a way. Wow.
Yeah. So it's sort of like, what's that scene in The Lion King when Mufasa is showing Simba, see, all of this is going to be your land, and he's like, well, Dad, what about that shadowy area over there? He's like, we don't talk about that. So that it's like that, but that's the inside of a black hole. We don't talk about that. That doesn't exist.
Well, not necessarily that we don't talk about it. It's that we know what exists. Like, in my view, like a black hole is the edge of a black hole, and talking about stuff like, we just fetishize Euclidean geometry. We think, just because something, like if something has a hole in it, there must be something in it. It's like, no, a hole can just exist as a hole.
So when we're talking about things like the what was that limit you said earlier? The
Chandrasekhar limit.
Yes. So is there a limit with the knowledge that our listeners can have about black holes? Have they reached that limit?
Oh no, you could Google for years.
I know.
But
no.
Here's the way that I'm thinking about it, though, is that if we have a mug, let's say we painted a design on the mug.
Yes.
What design do we paint on the space between the handle and the mug? We can't paint anything on it.
Correct.
In the same way, to me, black holes don't exist. Of course, they exist because they have a boundary, just like the mug handle has a boundary. Yep. But talking about what can be painted, it's like how many angels can dance on the head of a pin, that old medieval question.
Yep. Okay. So you need that hole in the handle to pick up the mug. So we need black holes. It's like, man, that's just weird.
And you could probably disregard some of that stuff, but like I said, that's my personal theory, and it might not hold up to scrutiny, but I don't know. I'm letting you guys know what I think.
Yeah. I guess my point earlier is, if we had much more of this podcast, it would be like my brain is all full, so my brain would just like get bigger, but because of the pressure of my skull, it would just explode.
And of course, the radius of his brain would equal the amount of mass energy that created that information, because it's a black hole. I don't know.
Yeah, something like that. Whew. Okay. So is that it? Should we bring our discussions on a black hole, at least in terms of talking about the current models, to a close, and just say something hokey like, well, don't take my words for it. I said words, so not to be confused with a certain show on channel, on PBS.
Oh, the one with LeVar Burton. That's not the one you're talking about.
No, it's not. No. So
Reading Butterfly or something?
Yeah, Reading Butterfly. Exactly. So with respect to black holes, we're going to end this, by saying after 3 long episodes and talking about, whether information is conserved, I like it. I'm just going to say, don't take my words for it. Google it yourself. You guys are smart with the cell phones and the Google and all that. Yeah.
Now we're going to just talk about some fun things about black holes real quick.
I agree. Fun things with black holes. Jonathan, I can't wait to hear what you have to say about this.
I wish you guys could see the expression on Gabriel's face because it's one of utter exhaustion.
Oh my gosh. Yeah, I feel like Rick and Morty. What was that one clip from Rick and Morty? What episode was it?
Oh, you mean this clip?
Yeah, where they were just like, he couldn't handle it, all the pressure. That's how I feel after trying, like there's so many weird concepts with black holes. I just feel like it turns your brain inside out and then like grinds it to a pulp, it's a lot to take in, man. It's a lot to take in.
Yeah, we're just going to talk real quick about some fun, I keep calling them fun things. Maybe I should stop. But one thing, like black holes we've talked about before, they radiate a lot of Hawking radiation at small scales. So it's possible to use a 1 ton or like a 1 million, I don't know how big it would have to be, but a black hole as energy storage. Just move it around using particles and like beams and stuff. Maybe if it's a charged black hole, use virtual particle interactions using electromagnetism to move it around, something like that. And you could create a spaceship that turns all of a certain amount of mass into energy. Because remember, a black hole turns all of its mass into energy. So as it goes through the universe, it could just pick up energy and throw it into the black hole, like the furnace.
The way you're talking, Jonathan, you're reminding me of like sci-fi. I'm thinking of 2 things. The first thing I'm thinking about is all the instances in sci-fi, in popular sci-fi, where black holes are mentioned. Now, I can name a few. I can name, Star Trek episodes. Is it Star Trek where they've got red matter that turns things into a black hole?
Oh no.
Okay. Is it Star? I think it is. I think it's.
I don't know, but it sounds like one of those Star Trek things that I wish didn't exist because I love Star Trek.
They just fudge it. The other one is it's mentioned in Rick and Morty as well, where Rick is bragging about his intellectual prowess, and he says, "Morty, I can turn a black hole inside out," or something like that. Which
yeah, which is called a white hole, which is a region of space in which nothing can enter, nothing can exit.
So the first thing I'm thinking about is when black holes are mentioned. But as you're talking about these hypothetical scenarios with black holes, I'm wondering about some black hole fiction. Have you ever wondered about what it would be like to write some science fiction about black holes, Jonathan?
I have not, but if you have, as a listener of Breaking Math, we'd love to hear from you. Okay. Send your black hole stories to breakingmathpodcast@gmail.com. And if you send a really good one, we'll read it on air and we'll just make it a special addition to our podcast. We'll credit you and everything.
Man, I want to read some black hole stories, like some film noir about black holes, or like a murder mystery with black holes, like, they say don't stare into the abyss because the abyss will stare back into you. So like, the way I interpret that is don't go sitting next to a black hole on a bus. You know what I mean? Like, that'd be weird.
Yeah, and of course we ourselves as Breaking Math would create fiction about black holes, but we're far too dignified for that, and you will never see any production of Black Hole Heist coming out soon in about a week.
Yeah, that's right. It wouldn't be us who does that. I mean, I don't imagine who it would be.
But here's another weird thing, because any mass energy meaning mass or energy stress, if you look at the tensor in general relativity, creates gravitation, meaning that light itself creates gravitation, meaning that if you send a photon out with the wavelength of the Planck length, and remember, the shorter the wavelength, the higher the energy.
Yeah.
And the Planck length is as short as you could possibly be in this universe, no matter what kind of yardstick you have. You would create a black hole going the speed of light, or almost the speed of light, I'm not totally sure, with a Planck mass, which is about 21.8 micrograms, which would have as much energy as a large tank of gasoline.
Wow. This whole idea that you can create a black hole with nothing but light, that is just insane. Again, I guess it makes sense because light and mass are different versions of the same thing is proven by Einstein's theory. Wow, it's nuts.
Yeah, and of course we already talked about helium and how it would be like normal matter but made out of black holes.
Yeah.
And there's just so many potential things, because in the primordial universe, when stuff was really, really high energy, small black holes probably were created all the time. So it's very possible that in that froth, all the dark matter, which dark matter and dark energy together account for like 90% of the mass energy in the universe.
Yeah. So you're saying one of the theories is that dark matter is in fact helium, or rather black holes that just will never ever evaporate. That's nuts.
Yeah, and of course all of that is very theoretical, and I guess there's so many experiments to be done on things like the LHC, which can tell us about high energy conditions. There's new experiments to be devised, maybe an entirely new type of thing that could be scaled like a accelerator. Maybe in 40 years we'll know about a black holerator or something like that.
I like that.
Physics is honestly just talking about sci-fi, but then doing it in the lab at the same time, and flying by the seat of your pants and going to conferences and arguing with people, and it's all very, very colorful.
Awesome.
Black holes seem bizarre, but not as bizarre as the fact that out in the uncharted backwaters of the unfashionable end of the western spiral arm of the galaxy lies a small, unregarded yellow sun, and orbiting this at a distance of roughly 92 million miles is an utterly insignificant little blue-green planet whose ape-descended life forms are so amazingly primitive that they still think digital watches are a pretty neat idea, but have ascertained the existence of a so-called exotic object which exists at scales far outside of their experience. And as we consider what we've learned, let us marvel at the fact that we're living in a world where new mathematical zeros and infinities, such as those found in and around black holes, are found, and that we've already harvested undreamt of bounties from this nearly God-forbidden information. I'm Jonathan.
And I'm Gabriel.
And this has been Breaking Math. Gabriel, do you have anything to plug?
So, actually, a few things. I think I plugged last time the fact that I'm still working my way through a great fan fiction book called Harry Potter and the Methods of Rationality. I'd love to do a podcast on this. I don't know that I can. I need to look into the legality of that aspect, but we probably can. I'd also like to plug some ideas for future podcasts. I really want to get into economics. I had a discussion on Facebook that was on, somebody had posted a video. The essence of the video was on socialism. And it said, in essence, socialism is not all that bad. It's been misunderstood. It's been misrepresented, et cetera, et cetera. The comments in this video were pure vitriol, like so much hatred. Now, the reason why I want to bring this up as a discussion is I'd like to talk about models of economic stability, and I'd like to talk about how not only different nations do it, in terms of their economics, how much of it is influenced by the state and how much of it is influenced by, privatization, but also within the United States, I'd like to talk about how different states and their economies are diversified, how they relate to, the federal government as well as just the state government. All of that stuff fascinates me.
And at the heart of economics lies game theory, which is so simple that it wasn't discovered until like the 20th century, and even John von Neumann was confused by it.
Yeah, and what I love about this topic is I had mentioned earlier the whole the vitriolic exchange. Is that a term, vitriolic?
Vitriolic,
okay.
Yeah.
The vitriolic exchange, where people were like using horrible terms to talk about other human beings. Well, I want to break things down as much as we can into mathematical models. I'm very familiar with, let's say, fiscally conservative arguments for economic stability and individual rights and liberties. I'm also aware of ideas that, sometimes things are more efficient if they're done at a federal level. So without even going one way or the other, to be frank, I'm very interested in just discussing and then tearing apart different ideas about economics. And I am, obviously this will come down to math, but then what, the other question is, what assumptions do you make in your mathematical models? Good.
Yeah, and of course, if we're being mathematicians, we have to be able to accept conclusions. So even though we might not swing one way or the other, we might make some statements that would seem to some people as controversial. So we're not maybe doing that next episode, but we might be.
Yeah.
So keep on look out for that, because we're definitely going to do it at some point in the future.
Yeah, it'll be dude. After doing this 3-parter on black holes, my brain, it feels like it's scrambled across the edge of the event horizon. My brain is. We definitely need a palate cleanser. So I just thought talking about economics would at least be invigorating and interesting. You know what I mean? Like.
Oh yeah, definitely.
Yeah, and the way that I've wanted to do it with my friends across the political spectrum is I'd love to talk about any model and talk about it like, as though I'm trying to sell you on it, but then also talk about the critiques, like even like Karl Marx. Even for those who are very opposed to communism, they say, well, he certainly addresses some concerns with human behavior and critiques, even though somebody might not be a communist, they can still acknowledge what he said and why it may be appealing to some people. And then, the opposite's true as well. So.
Yeah, and in my opinion, one of them is more true than the other, but we won't go into that.
Yeah.
We also have the $35 Breaking Math tensor poster now shipping from Breaking Math. Just go to patreon.com/breakingmath and order yours today. And we're sorry, I think for like 5 episodes, we've said patreon.com/breakingmath podcast.
Yeah. Wait, it is Breaking Math. Wait, is it Breaking?
No, it's patreon.com/breakingmath.
Oh, that's right. We had some people actually send in a message and say, hey, you gave me the 404 error. There's no website there. And they're like, oh, I'm sorry. It's patreon.com/breakingmath. My bad.
We're professional people recording professional things with professional equipment, professionally.
Okay, so there's actually one other thing that I want to plug. I want to have my roommate, actually, who's my wife's cousin, called Josh. He introduced me to a game on his Android, on his cell phone, called Holio, in a game where essentially you play as a black hole.
Basically, you just play as a black hole against 4 other people. You start off small. The more you eat, the larger you get, until you're devouring the entire city, block by block, including other black holes if they're smaller than you are.
Wow! And I even saw you playing the other day, and you as a black hole caught on fire. So it's kind of like the firewall, sort of, not really, but awesome.
Correct.
Awesome. Well, thanks for bringing that enjoyment to this.
Not a problem. Thank you.
Awesome, Josh. We'll talk to you later, man.
But thank you for listening to our first successful 3-parter on Breaking Math. You're very appreciated as a listener. And until next time.
Break some math? Is that our new motto?
No.